Respected guest of the day, Dr. Mostafizar Rahman from RC Bose Center of Cryptology and Security from Indian Statistical Institute, Kolkata. So, sir, welcome to the 5 days online faculty development program on cryptography and blockchain that is scheduled from 14th of November to 18th of November. So, we are having on day 3, session 2, we are having guest with us, Dr. Rahman, sir. Let me introduce you first. So presently, Dr. Rahman sir is working as a visiting scientist at RC Bose Center for Cryptology and Security, Indian Statistical Institute, Kolkata. His area of research is classical cryptanalysis of symmetric key ciphers, analysis of symmetric key ciphers in quantum computing model, and for advanced cryptographic applications. He, before being scientist over here, he was a project linked. He worked in a project linked personnel at RC Bose Center for Cryptology and Security. He is also being a senior project associate at Indian Institute of Technology, Bhilai. He has worked on multiple projects, that is computing system security. He is one of the instructor for cryptography training program for weapons and electronic system engineering establishments, crypto training program for Bharat Electronics Limited. He has also just a minute. Yes, he has also an honorary research fellow at Qualabs Software India Private Limited, and so being a software engineering engineer at Fonato Studio Private Limited. Apart from this, he has completed his PhD in Computer Science and Engineering in Cryptology and Security Research Unit. He has completed his Masters of Technology and Bachelors of Technology from Aligarh Muslim University, Aligarh. And he has a numerous number of publications in the reputed journals and such as SCI and Scopus Indexed. So, as per the research talks, he has appeared as an expertise in the multiple places and deliver an expert talk on the in the area of cryptography and blockchain. So today we are having sir with us, and we just welcome sir to the session, to taking our invitation at the short notice. Thank you, sir. So, sir, can we start with your session?
Yeah.
Yes, sir. Over to you, sir. Thank you.
Thank you for the introduction.
Thank you, sir.
Thank you for inviting me. Pleasure to give it. So today we will just talk about this quantum attack on symmetric keys. Basically, we can see our cryptography. We can divide it into basically 3 areas, like symmetric key, there are asymmetric keys, and apart from them, there are some hash functions. So today we will focus on how this symmetric key will behave in the post-quantum world. So that means when we have access to a very large quantum computer or maybe very small quantum computer, in that scenario, what will be the performance, what will be the security issues, and how our ciphers will work in that world. So basically, we'll start today with a brief introduction, and then I will just discuss about some preliminary settings and all these things, like what we considered as an attack, and what are the basic attack models, and how we are actually discussing the attacks. So there may be distinguishing attacks, some maybe key recovery attacks. So we'll discuss about that, and then we will discuss about what extra power this quantum computation gives us over this classical computer, and exploiting and how we are able to exploit that to mount the attacks. Then we will discuss some of the ciphers on which these quantum attacks are mounted, and then we'll discuss a little bit about this resource estimation. So basically, this resource estimation is like, so there are some generic attacks, but how big should our quantum computer should be that this genetic attack should be we can mount this genetic attack. So we'll discuss about that, and finally I will conclude it, and we can discuss about this future disease direction. So basically in the 90s, the development of these quantum algorithms have started. So, and there are lots of quantum algorithms, but these three algorithms that I have pointed out, the source algorithm, Grover's algorithm, and Simon's algorithm, these three has a huge impact of cryptography. So, most of all these three source has a huge impact. So basically, asymmetric key is introduced in around 70s, 80s, and in the asymmetric key, the security is like is based on some incomplete problems. So is it like that? So it is like that some system will be broken if this problem can be solved using our systems. But source algorithm, what it does, it can factorize any number in polynomial time. We all know that in our classical world, the factorization problem cannot be solved in polynomial time. So based on that hardness of this problem, some algorithms have been invented and been proposed. But source gives us the power that you can factorize any number in polynomial time. So that means that problem is now not at all hard in the post-quantum world. So this in turn, what it does, in turn breaks all the crypto systems which are based on this hardness problem. And then there are, so source algorithm has basically impact on the asymmetric key cryptography. These Grover and Simons have the impact on symmetric key cryptography. So Grover's is like a searching algorithm. So I will discuss it later in the Grover's algorithm part. So Grover's gives a generic attack on this symmetric key cryptography. And later on in 2010s, after 2010, it has been found that Simon has even bigger impact on some of the cryptographic motion, systems and all these things. So Grover bring down the can bring down the attack complexity, but it cannot bring the attack complexity from exponential time to polynomial time. But Simon has the power to bring down the attack complexity from exponential time to the polynomial time. So we'll see that basically our talk today is focused on how this symmetric key cryptography is vulnerable to this quantum algorithms. And based on this, so today, so now a competition is also going on, that is the NIST post-quantum standardization, because of the fact that many of the schemes that are already theoretically broken in the post-quantum world. So nowadays a new challenge is there, that define something, build some system which will be secure in the post-quantum world. So basically, earlier suppose people have designed some crypto systems based on factorization problem. So that is broken now in the post-quantum world. But if we now define some problem based on the hardness of some problems, which is also not breakable in the post-quantum world, then that should be secure in the post-quantum world. That is the idea. So based on that, NIST PQC standardization is currently going on. And this includes, I suppose many of you have heard about this lattice-based cryptography, code-based cryptography. This is a part of this. So we'll move to our preliminary discussion first of all. So first of all, we'll discuss about what is this oracle image. So classically oracle means that there is, suppose there is some function and I want the output. So I will just give the function x input and the function will return us the output fx. But suppose consider it as some secret function. So there is some secret key and function is using that secret key to give me the data. So for x, I cannot compute the fk of x, or in this example, ok of x by myself. So what I can do, I can pass this x to the oracle and it will return me the okx. So this is the classical setting of the oracle. So in this setting, we are allowed to only query the classical queries. So I can query. So basically, what we see in our in what we see now, these are all actually classical queries. So think of it like two communication has been going on, and between Alice and Bob, and something they have shared a key, and we are encrypting something and sending this encrypted messages. So think of it like Alice encrypts using the oracle, okay? So and sending the message. So these basically our classical setting, all these things. Quantitative in contrary to that, there is some quantum oracle. So in the quantum oracle, everything is same. So we are allowed to send some x, and we'll receive this order OK of x. But here, instead of classical queries, the queries should be in the superposition state. And this superposition state actually gives the quantum power. So basically, in superposition states, we can have the states can be superposition of any of the things, and this is the extra power that we are getting, and this power is exploited to mount different kind of attacks and to design those algorithms. I'll discuss about the cryptographic setting. So basically, what are the adversarial models, what are the attack models, what we consider as an attack. These things we will discuss now. So basically, these are the entities. So there should be a oracle, there is an adversary, and adversary has some computing powers. So what can adversary do? Adversary can send queries to the oracle, and oracle can send the responses. And what can adversary do? Adversary can use these responses and use his local computation power to mount some attack. Now, what is an attack? We'll see just. So there are various kind of attacks, and there are various things that can be considered as an attack. Now, these queries, so if he is making order of 2 to the exponential number of queries, so we can say that the attack complexity is much higher. And if he is making polynomial number of queries, so we can say that this attack complexity is lower. And even after these queries and all these things, so basically this is that we consider it as the data complexity. And after this, using the responses, he can actually do this computation in his local computer. Now here also, suppose here it takes some polynomial time, but it may be the case that to mount a successful attack, here using his local computer, he may need some more amount of time. Maybe this time is exponential. So if this time, so there is for every attack, there is some exhaustive search. So if the time is encompassing the exhaustive search, we generally don't consider it as an attack. So our target is to find something which is better than this exhaustive search using all these things. Now there are many assumptions here, like how this oracle should behave, what power this adversary should have, and what this local computation power he should have. This may be a quantum computer, this may be a classical computer, and what kind of power it should have. He can see only the responses. He can see these queries. He cannot make these queries. He only see that this is the query, this is the response. He can make these queries. So you can see that when he is only see the responses, he is not able to see the queries. And another scenario, he is able to see the queries and the responses. So obviously in the second setting, he has more power. Then he has more power when he can actually choose these queries and get these responses. Then we are assuming that he has more power. So basically, there are some assumptions. How much power should the adversary have? And on these settings, we try to define our security of these systems and all these things. So generally, these adversarial models, these are defined as Q0, Q1, and Q2. And apart from that, there is another model, just Q3, so which is not considered as a realistic one. Even Q2 is not considered as realistic one by some people, but still it is in the use. So there are 3 models. So discuss about these models. So in the Q1 model, we assume that adversary have only access to this classical computer. So this is the classical computer. This is not a quantum computer. And this oracle is also a classical oracle. So that means he can send classical queries to it, and he can get classical responses to it. So basically, the classical attacks that we see for our crypto systems are all part of this model Q0. Next, this is part of the quantum models. So in the Q1 model, the oracle is classical. So he can make here classical queries, we can get here classical responses. But we assume that he has access to a quantum computer. So in the responses, he will get the classical responses, but accumulating those responses, he can use this quantum power to mount some attack. So here is the advantage he is getting. So this is considered as the most realistic one because uh, implementing this quantum oracle is not very much realistic, and there is a question about in the community that why should anyone uh, give why should anyone design a quantum oracle or quantum systems in which will accept this superposition queries and everything. So at this point of time, many people think that if we replace this classical model with oracle with the quantum one, this is not a realistic one. But he has the computing power. This is considered as the realistic one. Next is the model where everything is quantum. The classical oracle is replaced by the quantum oracle, and the adversary has some quantum computing power. So now he can make here superposition queries. He can get the responses which are also in the superposition states, and then he can use this local computation power which he has, and it is a quantum computer, and he can exploit the power of this machine to mount some attacks and show that some attacks have been done. Next there are some attack models. So these related to the power of the adversary. How much power we should assume for the adversary when we will consider some attacks. So basically there are mainly these 6 kind of models. So first one is the very basic one where we assume the adversary has the lowest level of power, and that is the ciphertext only attack. So here we assume that adversary can only see the ciphertext. So if we just move to this model, so we can assume that here this adversary is only able to see these responses. He is not able to see these queries even. He cannot make the queries. He is not able to see the queries. He is only able to see these responses. In the non-plain text attack, we assume that adversary can see the ciphertext and the corresponding plain text. So someone else has queried to the oracle for x and get the value order OKX. So what can adversary see? He can see the value x and OKX, but he cannot make the query x. So little bit power is in the chosen plain text attack model. We add some more power to the adversary now. In this case, what adversary can now choose this x. So in the non-plain text attack, he cannot choose the x. He can only see that someone else has queried. He can only see this x and OK of x. But here he can choose his own x, and he can query the oracle, and he can get the outputs. So here again we are giving some more power to the adversary. Next, in the adaptive chosen plain text attack, now we are giving some more power. So here adversary in the chosen plain text attack, adversary are generating some x1, x2, x3 and querying them to the oracle. Now this x1, x2 and x3 are totally random. They have no relation to each other, and they are not dependent on anything. But in the adaptive chosen plain text, what happens? Adversary suppose queries x1 and receives some ciphertext, and based on the ciphertext, he decides what should be the value of the x2. So in the chosen plain text data, x2 is not dependent on x1, but in the adaptive chosen plain text data, x2 is dependent on the x1. So that is why the adaptive comes. So here he can choose the plain text, and beyond that he can actually make his choice based on some outputs he has already seen. Now all these 4 attacks are based on encryption oracle. When talking about x and OK of x, we are talking about like encryption oracle. But beyond that, there is some more power, that is the decryption oracle. So that is the power given by adaptive chosen ciphertext attack. So in the adaptive chosen ciphertext attack, we assume that adversary have access to both encryption oracle and decryption oracle. So now he can, suppose he query x and get OKX, and after receiving OKX, he computes something and generates some new ciphertext and query it to the decryption oracle to receive some new plain text. And based on that, he decides something. He takes some decision. So here, the adversary has more power. He can query to the encryption oracle as well as the decryption oracle. And this is the here is the most power is assumed for the adversary, and this is the related key attack model. In this model, we assume that adversary is able not only able to query to the encryption oracle, we also assume that he can send some key difference to the oracle. So basically, adversary will give some x and del k, the key difference, and oracle will give him the encryption of x and encryption of x when k or del k is used. So he will get a pair of ciphertexts. So this is the most powerful. So what is important here? Why you are actually? What is the motivation behind choosing these models? So generally in the community, people. So in the community, it is like suppose we are trying to prove some security in this model, chosen plaintext model, and if we have proved that security, that means this is if something is secure in chosen plaintext model, that means that this is also secure in non-plaintext model and ciphertext only model. And in this way, if we are suppose we are able to prove something that something is secure in this model, so that means these are all secure in this model. So basically, these are all used uh, for analyzing the security and all these things. And they have practical scenarios to it. So suppose like the related key attack. So how is it useful? So there may be the case that you have some embedded devices and on that some key is embedded and that key is doing this encryption. But using some fault or something from the outside, you are able to change the key. You don't know the value of the exact key, but you are able to change the key and you know the difference. So in that scenario, the related key model becomes relevant. So these are all have practical analogies to it, all these models, and these are all useful for analyzing the security and all these things. So just take an example for this model. So this is a one-time pad. So this is one security system used around I think 1920s or 30s. So in this maybe prior to that also. So in that what we did actually, what they did, they take some plain text and there is some secret key and XOR it to get the ciphertext. So usually here there are many problems of this scheme. So just forget about those problems because this key should be as long as this plain text. These are the problems. So just we'll analyze that how these attack models are relevant for this kind of things. So you can see that how this ciphertext is generated. We just take so this key is generated and this key is XORed with this plain text to generate the ciphertext. Now we'll see that whether this OTP is secure in the ciphertext only attack model or not. So suppose I am receiving this ciphertext 1101100. Can we say anything about the key or something? I think we are not able to say anything because using this ciphertext we are not able to say anything about the key or anything. So we can say that yeah, it is secure in this model. But now consider this OTP in the known plain text attack model. Now we in the known plain text attack model we know the plain text and we know the ciphertext. So our plain text here is this and ciphertext here is this. Now you can see that this should be vulnerable. Why? Because we know that the C is equals to P or K. So using that we can actually compute the K. So that K should be P or C. And as we all know the value of P and value of C, we can actually recover this key. So basically this OTP is secure in the chosen ciphertext only attack model, but it is not secure in the non-plaintext attack model, and which means that it should be vulnerable in all other stronger models, like in the chosen ciphertext, chosen plaintext model, and adaptive chosen plaintext model. In all this model, this OTP should be vulnerable. Now, what do we consider as an attack? So basically, I'm talking about this attack. So what is this attack is actually? So basically, we consider these three kind of attacks. There may be some other also, but mainly these three: the distinguishing attack, key recovery attack, and the forgery attack. So in the distinguishing attack, adversary based on the models, attack models like chosen ciphertext model or chosen plaintext model or adaptive chosen model, whatever may be the model. Based on this model, adversary sees some outputs. In the distinguishing attack, when you consider an attack as a distinguishing, so seeing this output, so when we are designing some cipher, our intention should be that adversary will not be able to distinguish the outputs of those ciphers from the random ones. So using those outputs and all those things, he will be just confused. He cannot distinguish whether it is a random or it is coming from some specific some cipher or all those things. So when we consider it as an attack, we consider it attack whenever adversary should be able to predict some outputs. So whenever he is able to distinguish, he can predict something. He can predict some next outputs in considerable time. In considerable time means that should be lesser than the exhaustive search. In the key recovery attack, as the name suggests, adversary can directly recover the key. So this is the highest form of attack. So you can recover the key, it is everything. In the distinguishing attack, he can predict the next outputs and all this. But in the key recovery attack, if he recovers the key, he can predict any number of outputs and all those things. So this is the highest form of attack. Next is the forgery attack. So this is in the some other thing like so this for the authentication. So usually when we say that Alice, suppose this is Alice and Alice is sending some ciphertext to Bob, but there is some adversary Eve. What he does, he just change the message. She just attack the channel. She cannot know the plain text. But what he does, he gives some, he do something and he change the message. Now Bob receives the message and he decrypts it, and he will see, of course, the some some message which is not valid, which is not sent by Alice. So how we can ensure that Bob receives a valid message that has only been sent by Alice, and that hello.
रजिस्टर ਤੇ ਲਿਖ ਲਓ ਰਜਿਸਟਰ ਤੇ ਲਿਖ ਲਓ ਚਾਹੇ ਅਪਲੋਡ ਕਰ ਲਓ ਐਗਜ਼ਾਮ ਜੀਐਨਡੀਸੀ ਦੀ ਨਹੀਂ ਹਜੇ ਖੁੱਲਿਆ ਨਹੀਂ ਹੈ
Participants, can you please keep your mic on mute?
ਕਰਨੀ ਮੈਨੂੰ ਦੱਸ ਤੁਸੀਂ ਕਰ ਲਈ ਆਨਲਾਈਨ
Just a minute, sir. I think they have kept their mic on mute. Yes, sir. Sorry for the disturbance. Please continue.
Okay. So okay. So basically, what can you do? She can tamper the message. But how we can ensure that Bob always receives the message? So she can tamper it, but how we can ensure that Bob successfully detects that whether his message has been tampered or not? So for that thing, what the design gives a special thing, a tag is attached with the message. So basically this tag is generated from the ciphertext. So this is that tag is dependent on the ciphertext. So when Bob receives the message, okay, so when Bob receives the message, what he does, he verifies that whatever ciphertext he has received and what tag he has received, he checks whether this tag is dependent on this message or not. If this tag is dependent on this message, he is then ensured that yeah, this message, this ciphertext has been sent by Alice and that has not been tampered with, and then he decrypts the message. Otherwise, what if Eve have tampered the message? What will happen? This tag will not match with this ciphertext, and in that scenario, Bob will know that his message has been tampered. So in these scenarios, what should be an attack? In these scenarios, the attack should be Alice can tamper this message when he can tamper this message only when he is also able to change this tag significantly. That means she sorry, that means she can tamper the message, and she can also she also needs to tamper this tag also, and that tag, the new tag, should be dependent on this ciphertext. So when Bob will receive this new tag and ciphertext pair, he'll first check whether this tag is dependent on this thing or not. So of course, if he is able to do it successfully, this test will be passed, and Bob will think that maybe this message has been sent by Alice. So this is called as forgery attack. So in this setting, basically the setting is like this, that Eve can query some messages to this to Alice, and based on that she receives some ciphertext and tag pairs, and based on that he tries to guess something. He tries to guess something, and based on that, now he can try to forge some new message or ciphertext and tag pair. And if it is passed as valid by the Bob, then she is successful. She has successfully forged. So this is the idea or notion of the forgery attack. Next, we'll discuss about the power of quantum computer. So what extra power this quantum computer gives us. So first we'll discuss about this Simon's algorithm. So if you consider any periodic function, so just consider this function. So this is a 3-bit function, input output. So this is the input and this is the outputs. So there are 8 possible inputs and 8 possible outputs. So you can see from here that 0, 0, 0 and 1, 0, 0 both gives this output, and both 1, 0, 0, 1 and 1, 0, 1 both gives 0, 0, 1 outputs. So you can see here that there are some periods in this function, right? And what is the period? This is the period 1, 0, 0, right? So whatever 0, 0, 0 gives, that's why 1, 0, 0 gives. So as 1, 0, 0 is the period, that is why this gives the same output. Now, how we are actually computing this period classically? So classically, we need to see all this input and output, right? So basically, this is a 3-bit function. So there will be three total number of inputs. So we have to query all this to the. So if we consider this f as an oracle, so we have to query all these x's like 0, 0, 0, 0, 0, 1 till 1, 1, 1 to the x, to the function f, and we have to receive this output, and only after seeing all these outputs we are able to decide what is the period. So basically, for computing the period in this case, we need order of 2 cube queries. What about this n-bit function? So if it is an n-bit function, then we need to make order of 2 to the n queries to f to recover the period. You can see that classically, when you're trying to solve this periodicity problem, when you try to just recover the period, we need to make order of 2 to the n queries. Now, what extra advantage this Simon's algorithm gives us? So I'll not go into the details of this quantum computing. I'll just give it as a brief overview. So what extra power it is giving. So basically, quantum computing gives us the power that we can solve this problem in polynomial time. Basically, we can solve this problem by making just order of n queries. So classically, this problem can be solved in order of 2 to the n. Using quantum computer, we can solve the problem in order of n queries. So it has brings down the time from exponential to a polynomial time. We will exploit this thing. So this algorithm is very useful for mounting the attacks on classical crypto systems, basically symmetric crypto systems. Next, there is the Grover's algorithm. So what it does, so it solves the searching problem, but it is, if you're just thinking like Simon's algorithm, it is not that powerful in compared to the Simon's algorithm, because in this classically when you're searching something in a set of n, where n is equals to 2 to the power n, so we have, when you are searching on an average, we need 2 to the power n minus 1 queries.
फालतू FDB वाला
Any queries? Yes, continue.
मेरा देखिए कितना लेक्चर है, कितना कुछ है, इतना कर पाएगा कोई? तो बताइए तो मैं ये पागल टाइप का काम करते हैं लोग.
Okay, so so there are 2 to the n number of elements. So on an average, when we are searching, we have to, on an average, we know that we have to search for at least half the elements. So that's why on an average, you have to take 2 to the n minus n times, to n minus 1. But but Grover's algorithm, what it gives us the power, and it brings down the time to the n by 2. So basically, the problem that we can solve in classically in order of 2 to the n, it can be solved using the Grover's algorithm in order of 2 to the n by 2. So it has reduced the complexity, of course, but like Simon's, it has not been reduced to polynomial time. It has been reduced to the exponential, but of course it has been reduced. And this gives us some power. Next, we will see the attacks on Q2 model. So as I have already discussed, in the Q2 model, we assume that there is some quantum oracle. So adversary make quantum queries, and there is some quantum computer available to the adversary. So he can compute on his quantum computer, local quantum computer. So
what is the configuration of this quantum computer? It is definitely with higher configuration.
Actually, in this kind of attacks, when you are talking about this, basically we are not concretizing something. So we just assume that it has some infinite memory. So we give as much power as to the quantum computer. Okay.
So it is nearly logical.
Mm-hmm.
It is nearly logical because we are considering that memory is of infinite size.
No, sorry, I just something. No, not infinite, because the attacks I just so the attacks that we have will see there. Actually, here we need very less number of memories. Okay.
If
So
a problem, exponential time problem will reduce to polynomial time, then there will be definitely polynomial time reducibility applicable in terms of this type of attack.
basically, the power that quantum computer gives that. So if we can see the Simon's algorithm, using the Hadamard matrix, we can actually, using just one state, we can make a superposition of all the, so suppose there is an n-bit number. So using n qubits, we can actually create a superposition of all the states that are classically available. So for generating for storing 2 to the power n, we are actually need only n qubits. But we will not be able to see those. When we will be able to measure, we will only see only one of those states. And that is the power actually exploited by these algorithms. But here we will just see it as a black box type of thing. We're not diving into deeper all those things. But considering that, okay, Simon's algorithm, it can solve this problem in polynomial time. And basically it is solving the periodic problem. So it is finding the periodicity. So what we'll try to do, we'll try to set our classical algorithms, the cryptographic algorithms, we'll try to produce some periodic function based on the output of these oracles. And then we'll assume that, okay, Simon's algorithm is able to solve this problem and it is returning us some non-trivial period. And we will see that whether this non-trivial period is, we can actually do some attack using this non-trivial period or not. Am I clear? Is it clear or you are asking something else?
No, thank you. I got that.
Okay. So the attack overview is that, so we are we are actually looking it as a black box level. So what we're trying to do, we know that Simon's algorithm solves the problem of the period of finding the periodicity in polynomial time. So what we'll try to do, we'll consider, we know that there is some oracle output. So we'll try to use the oracle output and we'll construct a periodic function based on that oracle output. And when we will be constructing a periodic function, we'll try to put some non-trivial period in there. That should be a maybe this non-trivial period may be a function of some secret key. So when we'll apply the when we apply the Simon's algorithm on this, what will happen? It will give us this non-trivial period in polynomial time, and using this non-trivial period, we will show that some there exists some distinguishing attack or key recovery attack or forgery attacks. Okay. So that means that using this, we can actually attack the system in order in time. So first of all, we'll see an attack on 3-round fiesta. So this is one of the paradigm for block cipher design. So there are many paradigms for block cipher design, like there are substitution permutation networks. So this is one of the fiesta. So it has been seen that 3-round fiesta is vulnerable to quantum attacks. So first of all, we'll see that what is this 3-round fiesta is. So if we consider only 1-round fiesta, we'll see that suppose these are the inputs, XL and XR, and this R1 is some secret function, or it is a function based on some secret key. So we don't, if even we know the input of XL, we don't know the output of R1. So this is the P1 and Q1. So as from the diagram, it is evident that this Q1 is equals to XL, and this P1 should be equals to this XR R1 of XL. Next, we extend it for 2 rounds, and in similar way, you can see here this Q2 should be equals to P1, and from the earlier expression, we know that P1 is equals to XR of R1 XL. And similar way, we can get the expression for P2 also. P2 is basically here Q1 XOR R2 of P1, and we'll get this expression. Next, we'll extend this for 3 rounds, and here we'll see that again wire is there, and this is basically nothing but P2, and P2 is basically Q1 XOR P1 or R2 of P1. And this is the final value. And in similar way, we can calculate the YL. Here our point of interest is on the basically YR. So we'll use this YR to mount the attack on 3-round fiesta. So basically, so what is happening here? So when you are actually, so you can think of this as an oracle. So what is happening here? We are giving oracle input XL concatenated with XR, and we are getting the output YL concatenated with YR, and from there we are receiving this YR. Now this YR, how can we construct? So our next step is to use this output YR to construct a periodic function. We have to construct a periodic function using this YR. How we can construct that? So you can see there that this function is there, R2 X R1 alpha beta. So just take this function. So we know the YR, value of YR, and as XL is given by us, so we also know the value of XL. So if we just take YR XOR of XL, we can get this value, and we'll show that this value, this function is actually a periodic function. So if we just construct this function in this way, if B is or X, where B is this value, so basically there can be only 2 values of alpha. One is alpha 0 and alpha 1. will show that this is a periodic function. So you can see that when this value is f0x, this is nothing but R2 of x or R1 and alpha 0. And this can be written as, we can just write here x R1 or alpha 1 R1 0. This we can write this. Now just if you take this now as the x, you can you can consider this now as a new x, and we know that for b equals to 0 we are taking alpha 0. So when b equals to 1, there should be alpha 1. So this is nothing but f of 1 XOR R1 alpha 0 and XOR R1 alpha 1. So you can see here that f0x is equals to this one. So what should be the period? So basically, if this is b XOR 1. So the period here for the first part is 1, and for the second part period is R1 alpha 0 and R1 alpha 1. So this is our period. So basically, what is the setting here? So using the YR, we are constructing a periodic function, and if we give this periodic function to some Simon, if we apply the Simon's algorithm to this periodic function, what will happen? We'll receive this output. Now the next question should appear to your mind. So there is some problem earlier. This attack was actually proposed by Kuokado and Mori. So in point of quantum computing, there is some problem in those initially in those attacks, because in those models, this wire and wire should be entangled. So you cannot see the wire. You cannot just make came out with the wire. You cannot just make wire and wire independent. So this solution was proposed by problem was solved by Hasuyamada and Sasaki, and they have introduced the idea of truncating output and show us how to just recover this wire independent of this wire, and then this attack is valid. So the next question that should come to our mind, that we are getting this value, yes, 1 R1 alpha 0 and 0 of R1 alpha 1. So 1 is just, you can omit this one. So basically we are receiving this value. So receiving this value, how is this even an attack? Why we are getting this value? How is this even an attack? Does this qualify as an attack? Does using this we can do the distinguishing attack or key recovery attack or the forgery attack? We have to see this. So you can see that suppose initially we are querying alpha 0 and m, and we are receiving C1L and C1R. Next, we know that this C1R is nothing but R2 R1 alpha 0 XOR m and alpha 0, right? So now we can see that so basically we know that this is our periodic function. So this periodic function, so this function is equals to C1R XOR alpha 0. So basically we will try to use this value, the R1 alpha 0 and R1 alpha 2, this value to mount and distinguishing attack. So basically we will try to predict something now. So we initially have queried this value and we have received this thing. And so we know the value of C1R, and as we have done this query on our own, so we know the value of alpha 0. So if we just absorb this value, we know this value. And apart from that, so till now what we know this value and we know this one. Now we predict that if we query now alpha 1 and m XOR alpha 0 and R1 alpha 1, we will receive C2L and C2R, and we predict that this value of C2R should be equals to C1R XOR alpha 0 and alpha 1. So basically we are predicting something. So this qualifies now as a distinguishing attack. So now if this our prediction is true, then we know that we have been successfully able to mount a distinguishing attack. So now we can check that, yeah, this value should be C1R. Why? Because basically C2R is nothing but, you just put the value of C2R in here, you'll see that this is nothing but R1 alpha 1 XOR this value. And and from what we so basically this means that R1 alpha is repeated here, so we are just XORing. So in the inside, just m XOR R1 alpha 0 should be there, and this is nothing but this value C1R XOR alpha 0. So that is why we can, using this value, this red value, see R1 alpha 0 or R1 alpha 1, that we have, that is the output of the Simon's algorithm, we are able to mount a distinguishing attack. And what is the complexity of this attack? So basically this thing we are, so after getting the output of the Simon's algorithm, we just need to make 2 queries. So the complexity is based on the complexity of the Simon's algorithm, and that is why this can be solved in polynomial time. So that means this 3-round fiesta is broken in the post-quantum world. Next we see another attack that is based on tweakable block cipher, LRW scheme, and this is the diagram of the scheme. So basically there is some secret key function EK block cipher and the plaintext is encrypted in this format. So there is some tweak T and a hash is used to generate this H of T, and before encryption and after the encryption with the output of this function, this HT is stored. So basically C is nothing but this P XOR encryption of this P XOR HT, that is this value, and the XOR of HT. Now we'll see that whether this LRW scheme is vulnerable to quantum attacks or not. So this was provided in 2016 crypto paper by Kaplan et al. And they have constructed the periodic function in this manner. So basically you can see here, this is repeated 2 times here. So basically this is XOR 2 times. So X is there 1 times, we are taking the value of T0, and for another instance we are taking the value of T1, and we are just joining the 2 instances. So basically if we think in terms of oracle, what we need to do? In terms of oracle, we are passing some X and T0 to the oracle, we are taking the output, and in the next instance we are passing X, the same X, and T1 to the oracle and taking the output, and we are XORing those 2 outputs. So we are basically using 2 oracle outputs and XORing them to construct this function. Now we'll see that whether this function is periodic or not. So if we just replace here X with X, HT0 and HT1, we'll see that this HT0 will cut out, and here it will be replaced by X XOR HT1, and it will be replaced by X XOR HT0. So basically the function will remain so this will remain almost the same. It will remain exactly the same, not almost, exactly it will remain the same. So basically f of X XOR HT0 and HT1 is nothing but fx itself. So that means this is a periodic function. So based on the oracle outputs of LRW scheme, we are able to construct a periodic function. Now what will happen? If we just give this, if we apply the Simon's algorithm on this function, what will happen? This is the period HT0 and HT1. Will be able to obtain the value of this thing. So we'll obtain the value of HT0 and HT1. Now again, why this is? So basically using the Simon's algorithm in polynomial time, we are able to retrieve the value for HT0 or HT1. Now why this is an attack? Now again, initially we are querying this T0, basically tweak T0 is there and a message M, and we are receiving C1. In the next instance, we are again using the same message and using the tag T1, and we are obtaining C2. In the next instance, we know that this is the tag, this is the value of the period, so we can sort this value with M and we can receive this value, and we are querying T0 or T0, the tweak, and this value to the oracle, and we are obtaining C3. Now we do our prediction. What we predict? That if we now query this thing, if we query this same plain text with T1 tag, we predict that the output C4 is nothing but the XOR of all 3 ciphertexts. How is this happening? You can just check that. We all know that. So we have seen that fx is, so we are, when we are taking the 2 output queries of the oracle and we are XORing them, that is nothing but x. So basically here, that is that should be m actually, sorry for the confusion. So that fm is nothing but the XOR of C1 and C2. And in similar fashion, this fm XOR HT0 and HT1, this should be equals to this value. and we know that this value is equals to C3 and C4. So basically, from here we can compute that C4 is nothing but C1s or C2s or C3. So using only these three queries, we can predict that, okay, we can know the value of the C4. So again, what is the complexity of this attack? So after this value has been recovered, we only need 3 more queries to the oracle. So again, the whole attack complexity is overwhelmed by the attack complexity of the solving the periodicity problem, that is the complexity of the Simon's algorithm. And again, the attack complexity comes down to order of n. Next, we will see an attack on XCS scheme. So this is quite similar to the last scheme, that is the LRW scheme. Only here you can see that the value HT is replaced by 2t.l. So the attack will be similar here. So I'm not just skipping this thing. So basically the attack will be quite similar. So one time we will use the tweak T0 and another time I will use the tweak T1 for encrypting the same message, and we'll just take the two outputs of the oracle and combine them to construct our periodic function. Next we'll apply the Simon's algorithm and we'll get just like in the last attack where we were getting the value HT0 and HT1, here we'll get the value 2T0.L and 2T1.L. And we can see that, like in the previous attack, we can show that this is a non-trivial value and this can be used to mount a distinguishing attack. So this is the typical Simon function actually, how we have shown on for this construction that how we are actually constructing this fx. So this is our periodic function. So first of all, I am querying this x using this value, the tweak T0, and we are receiving some output in here, and we are using this output as an input to the second function, second oracle query, and we have changed the tweak to T1, and we are receiving the output here. So this is the input, this should be the input of the Simon algorithm, and we'll apply the Simon algorithm on this thing. We'll retrieve the value 2 to the power T0.L and 2 to the power T1.L, and we can use this to mount the distinguishing attack. Next, this is a CBC MAC scheme. So this is one of those authenticated encryption scheme where a tag is being generated. So we'll again do the similar kind of things on this. We'll try to construct a periodic function, and we'll try to recover a non-trivial period. And here, in the last attacks we saw we are mounting a distinguishing attack. Here we'll show that how to mount using those non-trivial periods. We'll try to mount a forgery attack here. So how we are constructing here the periodic function. So again, we take this kind of we are trying to construct this kind of periodic function where so basically this alpha b is this m1. So you can see here there we are taking two block of messages, m1 and m2. So alpha b is the first block of message, and x is the second block of message. And you can figure out from the figure that the tag should be is basically nothing but ek dash of ek and this value, right? So here we are giving the 0, so that is why alpha b is or 0 is nothing but alpha b. And we are considering, so basically the output tag of the oracle, we are considering, we are using this to construct our periodic function. So you can see here that when we will just take f0x, the value should be, so b is nothing but alpha 0 here, and this should be here. And again, when we are taking f1x, this should be here. This should be the output value. So again, what we can do, we can replace this x with x or ek alpha 0 and ek alpha 1, and we will see that fbx is nothing but fb0 alpha b0 1 and x or ek alpha 0 and ek alpha 1. You can check this by just f0x replace this x with ek x or ek alpha 0 and ek alpha 1, or you can append here ek alpha 1 2 alpha 1 here, and you can then consider the first three terms as the x and the last term as the 1, and you will see that F0x is nothing but F1 x F1 comma x or ek alpha 0 and ek alpha 1, and this is the final output. So from here again we can predict, if we just give this function as input to the Simon's algorithm, what will happen? We will get the period, and what should be the period? 1 concatenated with ek alpha 0 and ek alpha 1. So again we know this value, so basically we can omit this one. So basically we know this ek alpha 0 and ek alpha 1, and again the same question, why even we will call this as an attack. So the first part is that just query alpha 0 and m1, and we predict that if we query alpha 1 and m1 and ek alpha 0 and ek alpha 1, the tag we get here should be a valid tag for this one. Why? Because again we can check in the similar fashion that the period is there, the period is ek alpha 0 and alpha 1. So basically we can replace this value and we'll get the same tag from the tag for both these will be same. So basically what we'll do, we'll just when we will change the ciphertext, we will just pass the updated tag for this. So we are able to force this new tag. So that is why it's successful as a forgery attack. Next, we'll see an attack on even Mansur cipher. So this is quite simple cipher compared to the previous one, but it has huge impact on cryptography. So you can also consider it as a one round AES. So what it does, you can see this P. This P is a public permutation. It's not some secret key permutation. This is a public permutation. So if you know this input here, you can always know the output here. But for making it a block cipher, what we are doing, we are actually encrypting, we are actually zoring some K1 with this message. So we are ensuring that this value is not known to the attacker, and we are taking the output and we are again joining some K2 with this, and we are receiving this C. Now again we'll try to see whether this is vulnerable to Simon's algorithm or not. So again our strategy is like we should try to construct a periodic function from here. So this is the oracle output P, M or K1 or K2, and we all know that as it is a public permutation, so we have access to it. So we can compute it on a local computer. So how can we construct the periodic function? We just take the output of this oracle and we XOR extra px with it. So basically this is our periodic function. So you can check here what is this function, fx equals to p of x XOR k1 XOR px XOR k2. Now if you just replace this value x with XOR k1, you can see that just the input of this 2p will be changed. So XOR k1 will be changed by x and x will be changed by XOR k1. So basically the when you are taking x as an input and when you are taking XOR k1 as an input, the output of f function is same. So what is the period here? The period is k1. So basically here, so in the earlier attacks we see that we are able to mount distinguishing attack, we are able to mount forgery attack, but here we'll see that this is the secret key. So we are actually get the output of the Simon's algorithm. The output of the Simon's algorithm is the secret key here itself. So this is the key recovery attack. So we are able to retrieve the secret key here. Now we can use the secret key to retrieve this key also. How? Because what you can do, we can take this NEM and we query the oracle to obtain some C. Now what we can do, as we know this K1 now, we have already got this output from here from Simon's algorithm. So we can compute this M or K1. So we know the output of this P public permutation. So as it is a public permutation, we know the output here also. So this is just like that one-time pad. Now this part. So we know the C, we know the value here. So we will just jot this value to obtain this K2. So we can recover this K1 and K2. So this event console is broken in the Q2 model. Now, like the event console cipher, there is similar construction, that is the effects construction. So you can see that everything is similar, only this P is replaced by EK. So in the event console cipher, there are only two keys, K1 and K2. Here we have three keys, K1, K2, and K. So we'll see whether the same attack is possible or not. So we'll first try to approach, we'll take the approach in the similar fashion we'll take for the event console cipher. So in the event console cipher, what are we doing? We are taking the oracle output and we are joining it with P of X. So similarly, we can do this here. But what is the problem here? In the event console cipher, this EK, this function was not secret. This was a public, so we can compute the value. But here, this function is secret one. We cannot compute this value on our own, and there is no oracle is there for this one. So although this function is a periodic one, and it has the period K1, but actually we will never be able to construct this periodic function, as this EK is not known to us. So basically, using the last approach, this attack will fail. We will not be able to do the attack. So we have to find something else. We have to take some extra advantage here. So, so that was, this was proposed around 2019. No, sorry, 2018 maybe. So here they proposed that to actually combine the power of Simon's and the Grover's algorithm. So earlier attacks we have seen that are only the implications of Simon's algorithm, but here we'll see amalgamation between the Simon's and the Grover's algorithm. So this approach is known as Grover meets Simon's algorithm, Grover meets Simon approach, and here we'll construct the periodic function in this fashion. So we don't know this I. So if we know this I, we can do the attack, but we don't know this I here. So this function, when this function is periodic, this function is not periodic for all values of I. Only this fkx is periodic. So this is the, when fk, if we are able to successfully find this k, only then we'll be able to recover this k1. So first of all, for constructing this periodic function, we have to successfully find this, the value of I. Now for finding, so there are, so if this is the k is of n bit, so there are 2 to the n possible values of k. So for finding, we can here take the help of the Grover's algorithm. So Grover's algorithm can find this k in time order of 2 to the power n by 2 instead of order of 2 to the n. And when we have been able to find this k, then we can apply the Simon's algorithm to recover this k1 in polynomial time. Now the attack complexity of course reduced here, but it is not reduced like the previous cases. In the previous cases, it is reduced from exponential to polynomial, but here it is still polynomial, but it is in the order of 2 to the n by 2. Next, we'll use this, the combination of Grover's and Simon to mount attacks on Q1 model. So as I've already told you that Q2 model, the oracle and the local computation model both have quantum computation power. But in the Q1 model, the oracle is a classical oracle, so the adversary only can make classical queries. But in the local computation power, he has access to a quantum computer. So basically now he cannot directly use the output of the oracle, as those outputs are not superpositions, and they are not in superposition states. So he cannot directly apply Simon's algorithm on those outputs. He has to do something on his local computer, and then he can apply Simon's algorithm on these things. So obviously the complexity will be increased now. So we'll just see the same attack like on the event console cipher, and in this format in the Q1 model. So you can see here that the key K1 that was initially there, we have divided into two parts. So first part is K11 and second part is K12. So in the you have just seen in the government Simon that how are we doing the attack, how are we mounting the attack. For one part we are searching using the Grover search algorithm, and another part we are applying the Simons algorithm. Here we will also apply the same technique. So for the first, we'll divide the key into this part, K12 and K1. For this part, we'll apply the Grover's algorithm, and for this part, we'll apply the Simons algorithm. And you can see here that we are dividing the we are dividing the message space in this fashion, in minus u and u. So for the Grover attack, here we need complexity in the order of 2 to the n minus u, and we can do it in order of u. So what is the function? So basically, this is our function. So what we have done here basically, we have kept these values, the message bits here as 0, all bits 0. So whenever it is going to XOR with K12, this is nothing but K12 itself, because all the message bits for this part is 0, and for this part we are taking the X. So basically we are applying the will apply the Simons algorithm only for this part. So you can see here. So these are public permutation. Also we have divided the input here also in u and n minus u bits. And if you see this whole thing, fix and gx, you can see that this is a periodic function. When this is a periodic function, when this value of I is k12. Only when this value is I equals to k12, this function is periodic, and at that time this value is, the period of the function is k11. So this is quite similar to the last attack on fx construction. Only the expression is now changed, but the setting and everything is same. So again, what we have to do? First of all, we have to apply the Grover's algorithm to recover this I to this value k12. So if it is n minus u bits, so we can recover it in 2 to the n minus u by 2 in order of 2 to the n minus u by 2. And for the rest of the part, once this has been recovered, for the rest of the part, we can apply the Simons algorithm, and we can recover the value of k11. In this way, we can concatenate this k11 and k12 after recovering both this, and we can get the exact value of k1. So why we are calling this as a q1 attack? So first question is like, why we are calling it as a q1 attack? So just see how are we actually constructing the function. So basically what we need to do here, so we are keeping these values as 0, all this. So basically this is our oracle, and we are querying this to the oracle. So this value was always set to 0, and for this u bits we are querying all values here. So 0, 0, 0, 0, 0, 1, all the possible values here we are querying it. So using that, so when we have all the values, so basically we have output of all these values, and now using all those outputs we can construct the superposition states in our local computer. So that is why we are taking here this exponential complexity. So we have to make here exponential number of classical queries to construct this equivalent superposition state in our local computer. But that is not the case in the Q2 model. There we are getting the superposition responses from the oracle itself. So we don't have to construct our own superposition states, and that's why we can do the attacks there in order of n time. Next, we will see some attacks on this quantum attacks on HTTR invariance. Just so there is no much time left. So I'll just give you an overview here. So this will look quite haphazard here, like quite complicated here. So just try to focus on this, that we are trying to construct a periodic function based on this C2. So what you're trying to do, so you can see the C2, the ciphertext output as this value. So there is some value for IV1, and we'll try to recover the value of this HHT XOR M2. So this pi2 is nothing but we are trying to retrieve the value of C2 only. So basically we are querying with some tag T0 and T1, and we are concatenating the Oracle output to construct this function. And you can see here if we just replace this x with XOR x XOR HT0 concatenated to M2 and this value, this output will be the same as the earlier. So basically this is the when we'll apply the Simons algorithm on this function, we'll receive this, recover this non-trivial value, and we can show that this can be used to mount some distinguishing attack on HCTR scheme. So in similar fashion, we can also so the earlier attack was in the Q2 model, and in similar fashion by dividing the input messages, we can also mount attack in the Q1 model. Next part is the quantum resource estimation of Grover's attack. So basically, Grover's attacks, as we have seen, that it reduces the searching time from order of to the n to order of to the n by 2. So the first implication of the Grover's attack is a generic attack on block cipher. So block cipher, there is a key of size k, and if you are doing exhaustive search on the key, we would need 2 to the k number. So there are 2 to the k possible keys. Now, if I want to recover the key, so you can use this Grover's algorithm, and we can recover the key by making order of 2 to the k by 2 queries. So this is the extra power that is Grover has given. So this is a generic attack. So initially people were thinking that only Grover's algorithm has impact on symmetric cryptography. So this was the impact actually. So there was a generic attack on block ciphers, but later it was found in 2010 that no, actually it can have more implications. The quantum computation can have more implication on the symmetric key cryptography, and that is the impact of Simons algorithm. So this Grover algorithm can also be used to mount attacks on hash functions. So basically, in the classical setting, the hash function in the generic attacks, we have order of 2 to the n by 2. We have attacks, but based on the Grover's algorithm, an algorithm that is Brassett-Ware tap algorithm, the BHT algorithm was proposed, which can find collision on the hash function by making order of by making just order of 2 to the n by 3 evaluations. And that's why, so in the case for block cipher, it is reducing the reducing the space to the n by 2. So there was a general solution to this, that if we can just increase the key bits, increase the key size by double. So if we are in the classical setting, we are in the classical world, we are using key for 128 bits key. So if we just increase the key size to 256 bits, this will give the same security as the security given by 128 bit ciphers in the classical world. So similar way, it was the thinking that if we just increase the hash output by 3n bit, it will provide the same security as it provides in the classical world. Now, so for this block cipher, so we have seen that this Grover search as a generic attack. Using the Grover search, we can mount a generic attack on the block cipher. So, but the question comes that how practical is the attack? So basically, people are calculating that how big should be our quantum computer when we will be able to mount this kind of attack. So currently, as I have told, that currently NIST post-quantum standardization competition is going on, and they have specified some values on some parameters there. Okay, so they have some philosophy on which they have specified the values. And as of now, we don't have a working that big working quantum computer. So there are some prototypes of the quantum computers, but not that big. So, and it is not also standardized that what kind of computing power we can have in the future. So they have taken the consideration that we can design a circuit in the quantum computation model. So the circuits will be based on some gates, and we will. So basically, the idea is that we'll to mount a Grover attack on some block cipher or any of these things, we need to design a circuit, and we'll try to compute the theoretical values of this circuit, which will be able to mount this attack, and we'll get some gate counts, and we'll see whether these gate counts are less than this value or not. If the gate count for mounting the Grover attack is less than this value, then we'll think that these designs are vulnerable in the post-quantum world. So for 128-bit or for 128-bit ciphers, this is the exact value. For hash, this is the value. So suppose we are doing something, we are trying to analyze the security of present, suppose 128-bit present. What we'll do, we will implement the Grover circuit in the quantum computing model, and we'll calculate the gate count, and we'll see that whether this gate count is less than this value or not. If this is less than value, we can then decide that this may be vulnerable in the post-quantum world. And if this value is greater than, then we can say that this is secure in the post-quantum world. So in the quantum resource estimation of Grover's attack, we are basically what we are doing. We are the idea is to design a quantum circuit. Just I have told you that we have to design a quantum circuit for this mounting Grover attack on block cipher, and we have to estimate the resources. Now for the estimation purposes, there can be two approaches. Basically, you can take the any framework, you can take help of the framework, or you can do it also in mathematically. So mathematically, like you can design a circuit, and you compute for a small version, you compute the gate, and you can just multiply those values with the corresponding required values, and you can get the final gate counts. And in the framework versions, just we have used like these things, Project Q and this kind of frameworks. These provide us some automated resource estimation tools. There we only have to bother about designing the circuits. When we have already successfully designed the circuits, the estimation tools inside that framework will calculate the gate count for us and will provide the output. Now it has some extra advantage also, as claimed by this the designer of this frameworks, as they claim that when we are actually doing this theoretical calculation, the gate count, we can actually overcount some gates, and as per their claim, the gate count can be as lower as possible till now, not it is the exact lowest count, but till now as low as possible as per the claim. Now where this extra bound is getting, basically this framework, this analyze the circuit, and they try to reuse the resources as much as possible, and there we are actually getting some extra advantages, and that's why there are some other frameworks also. We are using Project Q, that's why I have mentioned it here, but there are some other like Q hash, and there are other languages also. So basically, what we have seen here, the security of key alternate ciphers. Basically the event 1 cipher is a key alternate cipher, and we have seen the security of these ciphers in the quantum computing models. And another thing is that we have already discussed that for achieving this m-bit achieving the m-bit security, we have to extend it, we have to double its key size. But till now, there are no work has been done whether keeping the same bit security, m-bit security, whether we will be able to resist quantum attacks or not. And the other thing is like that the framework for the resource estimation. So till now, people are considering some concrete ciphers like present, Katan, and AES, and all these things, some specific ciphers, and doing the resource estimation on it altogether indifferently. Now there is also a possibility like we can remove all those hard works for each ciphers, and we can create a general framework and which framework will actually estimate the resources for us. Then we have to don't do this repetitive work for altogether. We can just omit this repetitive work and we can analyze the security. So so basically this is the impact of till now, the impact of symmetric cryptography, impact of quantum algorithms on the symmetric cryptography. And thank you. Any questions? Hello, am I audible?
Yes, sir, audible.
Okay. So I am done. Is there any question?
Yes, sir. Thank you so much. So, is there any queries from the audience side?
Sir, how to simulation? Where to do the simulation?
Hanji, is there any queries from the audience side?
Hello.
Hello.
Yes, sir. Uh,
How to do
Dr.
the simulation?
How to?
How to do the simulation, or whether this is only algorithm oriented?
The resource estimation part.
Yes.
This part. No, the first part is only algorithm oriented, and you cannot do the simulation there because 128-bit we cannot simulate this. And for the resource estimation part also we can. I've tried to do it probably for 30 bits. Still we can do it in our local computer because it is taking too much time. 30 to 35 bits is fine, and after that it is taking a lot of time. So we cannot do the simulations here actually till now. So resource estimation, for resource estimation we do not need the simulation. We just count the resources. So we design circuit and we count the resources.
Thank you. Sir, any references?
Okay, references, actually I've kept it in my slides, in each slide. So this is our paper, and like this Bonnet et al., this paper by Bonnet et al. In by 2019 ACA Crypt, and the main paper, you will get the initial paper was this one, the paper by Kaplan et al. So this paper is like breaking the symmetric key crypto system using quantum QFID, and it was published in one of the top crypto conferences, that is Crypto 2016. So if you're interested, you can initiate from here.